Hello, hello, hello. Is the mic working? Hello. Okay, now. Okay. Is it working now? Doesn't seem to be. Okay. Now it's working, right? Fine. Topics. Top. Hello, 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 hello. Hello, hello. Okay, sometimes it's audible, sometimes. So the mic, sometimes it works and sometimes it doesn't. So if it stops working at some point, you'll have to let me know. It's probably an issue with Google Meet instead of my own earphones because these are new earphones, so there shouldn't be a problem. Usually, at this point of the course, people stop attending these live sessions. Only a few people will come. Even in bigger courses where there are 10,000 registrants, there won't be that many students. So I, I usually don't prepare too much for these sessions. I only prepare what is required. Anyway, let's start. Question 1. An information sequence is encoded using 7-4 Hamming code and received sequence R is 1001110, and this received sequence has a single error in it. The bit location of single error is so this week I should have okay some simple linear block codes 1 and 2. Second part had Reed Muller codes and you studied bounds on the size of a code. So you must have seen what a Hamming code is and the error detection and correction procedure. So Hamming codes are nice in that they're designed in a way that it is very easy to tell the tell where the error has occurred. So once you know the bit position in which an error has occurred, you can simply flip that bit and your error will be corrected. So for a Hamming code, if you arrange the columns in your parity check matrix such that your column I is the binary representation of the number I or the integer I. For example, if you here in this case we have a 7-4 Hamming code. That means there are 7 columns and 7 minus 4 n minus k rows. So in a 7-4 Hamming code, the parity check matrix, so column 1 should be the binary representation of 1, so it's 1 0 0. Column 2 is a binary representation of 2, then 3, then 4. So this will be your MSB and this is the LSB. 5, 6 and 7. So see, all these error correcting codes are only equivalent up to the bit positions. So if you change the bit indexes, right, it will still be a Hamming code. So if you rearrange these columns, whatever you get in the end will still be a Hamming code. So this is, it's not necessarily, it will still be a code, but whatever following property I'm going to tell you, that won't hold in that code. So to make decoding simpler, you have to arrange the columns in this way, where the column I is the binary representation of the number I. If you do that, then the syndrome that you get will represent the position of the bit error in binary. So if you arrange the columns such that you arrange the columns of the parity check matrix such that the column I is the binary representation of integer I, then if there is a single error, of course you can only collect single errors with this 7-4 code, then if you take the syndrome that you get is the binary representation of the bit position where the error has occurred. So let's do that in this case. The received message is 1001110. So R is 1001110. The syndrome is R times H transpose. So 1001110 times the transpose of that matrix 1000010 110 001 101 011 111. So you might have studied in linear algebra, if you have a vector that is left multiplying a matrix, then the result will be another row vector which is a linear combination of the rows of the matrix, and the coefficients in the linear combination will be the entries of that vector. That's just one way to multiply it. You could do normal multiplication, okay, but the way I like to do it is this will be the linear combination of the rows of H matrix, these rows, and you only pick those rows where there's a 1 in the vector. So there's a 1 here, so you will take 1 0 0. There's a 0 in the second position, so ignore this row. 0 in the third position, ignore this row. Then there's 1 in the next three positions, so you add these three rows. So you add 0 0 1, 1 0 1, 0 1 1, 0 in the last position, so ignore this. And that will give you the product of the row times the matrix. Of course, the addition should be in binary. So this is nothing but 100 plus 001 is 101. 101 plus 101 is 000. Plus 011 is 011. That is the syndrome. And this, if you treat it as a binary number, this is nothing but um, you have to be careful here. This is the MSB, this is the LSB. This number is not 011, it's 110. So in the sixth position, a bit error has occurred. Okay, this is not true for all codes. This is only for the Hamming codes, and especially when you arrange the rows columns of the parity check matrix in this way. If you interchange the columns, then the answer will be different, and if it's a different code, again this won't work. That's question 1. Let's move on to question number 2. Which of the code parameters are not correct? So the four options are a 6357 Hamming code, a 6155 shortened Hamming code, a 6356 expurgated Hamming code, or a 6458 extended Hamming code. So which of these has code parameters that are not possible? So if you have an NK Hamming code, then this n has to be equal to 2 power m minus 1, and k has to be equal to 2 power m minus m minus 1 for some m greater than equal to 3. So if you want to get a 6357 Hamming code, then n is 63, which is equal to 2 power m minus 1. For that you need 2 power m is equal to 64, which means m should be equal to 8. So if you want your n to be equal to 63, it is possible. So you have a Hamming code of code length 63, but the k would then have to be equal to 2 power m minus 1, which is 2 power 8 minus 8 minus 1, which is 2 power 7 is 128, 2 power 8 is 256. Sorry, it's not 8. 2 power 6 is 64, 2 power 5 is 32. So this is 6. So 2 power 6 is 64, minus 6 is 58, minus 1 is 57. So these code parameters are possible, 63 and 57. This is true for any Hamming code. N should be of the form 2 power m minus 1 for some integer m greater than or equal to 3, and k should be of the form 2 power m minus. Here 2 power m minus 1 is simply n, so it should be of the form n minus m. So this 6357 Hamming code is possible, so the parameters are correct. They're asking which is not correct, so we'll next have to check the other options. Second option is shortened Hamming code with parameters 61 and 55. So to shorten a Hamming code, you delete a number of columns of the Hamming code. So if you delete L columns of the Hamming code, let's see, by deleting L columns from the parity check matrix of an NK Hamming code, you will get an N minus L, K minus L shortened Hamming code. So the code word length is shortened here. Okay. Now we originally saw that we can have a 6357 Hamming code. So if you subtract 2 from both of them, so if you subtract 2 of the columns, you will get a 63 minus 2, which is 61, and 57 minus 2, which is 55 shortened Hamming code. So 6155 shortened Hamming code is also possible by deleting 2 columns from the parity check matrix of the 6357 Hamming code. So option B also has the correct parameters. Next we have to check option C, a 6356 expurgated Hamming code. So the code length is the same, but the number of message symbols is decreased. So you have the same number of same length code words, but the number of code words you are using is decreased, because if your message k is the number of message bits, right? If the number of message bits is decreased, the number of messages you are encoding, which is 2 power k, is also decreased. So if there is a one-to-one mapping between your messages and your code words, so if the number of messages is less, then the number of code words is also less. So in essence, you're taking a Hamming code and deleting some of the code words by adding an additional constraint on the code words. And that will be an expurgated Hamming code. You can do that by, say, if H is the parity check matrix of a Hamming code, then you can simply add a row of ones. I'll call this h1. So you take h and you add a row of ones to that edge. So here you take this and add a row of ones, and that would be an expurgated Hamming code. If you do that, so what does this mean? This extra condition, you have to remember what the property of a parity check matrix is. So in any code, if you take a code word and multiply that with the parity check matrix, then you have to get a zero vector, right? So it depends on the notation depends on how you write your code words. So if you are using row vectors, then ch transpose is equal to 0, where c is your code word. C is c0, c1 up to cn minus 1. And when you do ch transpose, it will be something like We'll have H transpose here, and then final column will be all ones. So the last column of this CH transpose is nothing but C0 plus C1 plus etc. Cn minus 1. And since this entire thing has to be equal to the 0 vector, this C0 plus C1 plus etc. Cn minus 1, this should also be equal to 0. Okay. Or if you write it in a column vector, if you write your code words in column vector form, then h times your code word should be equal to the 0 vector. So h times C0 C1 up to Cn minus 1 should be equal to 0 0 0 up to 0. So this last 0 comes from multiplying this last row with this column. So the dot product of the last row and the column vector will give you the last entry of the result. So C0 plus C1 up to Cn minus 1, that should be equal to 1, 0. So what does it mean to say that sum of the elements of a code word is 0? It means that the weight of the code word is even. If you have an odd number of ones, then when you add all the ones, you will get a 0, right? So if the sum of all the bits in a code word is 0, there must be even number of ones. So the code words are all even weight code words. So by adding this additional constraint, what you are essentially doing is so this parity check, for this parity check matrix H, you had some code words, some set of code words. It will have even weight code words and odd weight code words, a set of even weight code words and a set of odd weight code words. By adding another row containing only ones, you are saying that all your code words must be even weight code words. So you are taking away the odd weight code words and you are left with only even weight code words. So you are removing half of the code words, right? Because we had studied in the previous assignment, you had a question. If you have even and odd weight code words, then the number of even weight code words should be equal to the number of odd weight code words. So it reduce the number of code words to half of the previous one. So if you had x code words, now there are x over 2 code words left. That means the number of messages is also reduced by 2, because there's the one-to-one mapping between your messages and your code words. So the number of possible messages that you can encode earlier was 2 power k. There are k message bits. Now that has been halved. So you can encode 2 power 2 power k by 2 messages. That's nothing but 2 power k minus 1. So you can have only k minus 1 message bits. So this code is an n comma k minus 1 expurgated Hamming code. So if you have an nk Hamming code and you add a row of ones, you will get an nk minus 1 expurgated Hamming code. We had a 6357 Hamming code. So if we add a row of ones, we can get a 6357 minus 1, which is 56 expurgated Hamming code, right? So those code parameters are also correct. Okay. That means first three options have correct code parameters. The answer must be option D. But we'll check uh, and what an extended Hamming code is, what the parameters for an extended Hamming code are. So to get an extended Hamming code, you are in an extended Hamming code, you are increasing the number of code words. You're not increasing, you're increasing the length of the code words. So if you have a parity check matrix H for an NK Hamming code, so if H is your parity check matrix, then you can extend the code by extending the matrix as follows. So you take your original H matrix and you add a row of ones, and then you add a column of 0 followed by a 1. So this will be the parity check matrix of an extended code. And the parameters of this extended code will be, so here H will have n columns because it's a Hamming code from, it's an NK, it's a parity check matrix from an NK Hamming code. So you added one more column, the number of bits in your code word is increased by 1. So this will give you an n plus 1 k extended Hamming code. So we had a 6357 Hamming code. From that you can get a 6457 extended Hamming code. But they have said that you can get a 6458 extended Hamming code, which is not true. So 6458 is not the correct code parameter. So the answer is option 2. Okay. The third question, both RM13 and RM01 are self dual, true or false? I'll give you 2 minutes to solve this question, and then I'll come back and give you the answer. Okay, I hope you tried that on your own. I'll give the answer now. So, in lecture, you should have seen that for an rth order Reed Muller code, the m minus r minus 1th order rm code is its dual. That's just a property of Reed-Muller codes. I'm not sure if it was proven in class, but there you have it. That's the property of a Reed-Muller code. So, Reed-Muller code, the code length will be equal to 2 power m, and that's the m, and the minimum distance will be 2 power m minus r. Okay, that's the order r of the code. So for let's see, for the first code, rm of 1 3, so the r is 1. For rm 1 3, r is equal to 1, m is equal to 3. So m minus r minus 1 is 3 minus 1 minus 1, which is 1. Okay, so the 1th order rm code, so the m minus r minus 1th order, here m minus r minus 1 is the same as r, which is equal to 1. So the 1th order rm code is a dual of a 1th order rm code in this particular case, for that particular value of m and r. Okay, then you check for rm of 0 1, where r is 0, m is 1, and you get m minus r minus 1 is 1 minus 0 minus 1 is 0. So the dual of this code is also a 0th order rm code. So these both of them are self dual codes. So the answer is true. Okay. Uh, One more point here is that I've only shown that the dual code of one third RM code is another one third RM code, and the dual of zero third RM code, this particular 01 RM code is another zero third RM code. But I haven't shown that it has to be this particular RM code itself. So it could be some other code with one, some other M. So we have to show that. Um, so that will show that it is actually a self dual code. Okay. So keep that in mind. I'll show that a bit later. Uh, the solution I have with me now doesn't show that, it only shows this. So I'll come back later and show that. Okay, and we'll go to the next question. So what is the minimum distance of an RM14 code? So RM code is specified by the parameters R and M. So in this case, R is equal to 1, M is equal to 4. I'll give you 1 minute to solve this. It's just a simple formula. If you have seen the lecture, you should know. Do you guys know what the minimum distance is for a readme look code with parameters R and M? Yeah, 2 power M minus R. So d min is 2 power M minus R. Just 2 power 4 minus 1, 2 cube, which is 8. So the minimum distance for this code is 8. Okay. So you have to watch the lecture videos and then come to the live sessions, because of course if you have a doubt you can ask me, but I won't be teaching you any of the theoretical stuff. You have to watch the lecture videos for that. Okay, I'll give you my mail ID, and I have typed it out in the chat. In the next class, after you see the lecture videos, if there is some point that you didn't understand, you can let me know beforehand through mail. I'll go through that particular lecture. You'll have to give me the time with. You'll have to tell me which lecture it is, and which timestamp it is. I'll go through that particular section and uh, clear your doubt if you have any, because I won't be able to watch all the lecture videos myself. I am busy with my own work. So after watching the lecture videos, if you have any doubts in some point, in some portion, then you can send me a mail. I'll go through that part, and in the next problem solving session, I'll, after the session is over, right? This problem solving won't take the entirety of 2 hours, which is allotted. So once the problem solving is done, I'll clear your doubt, because all these things I studied like 2 3 years ago, so I won't be able to clear your doubt in an instant, because here in the previous problem, this Reed Muller code, I don't remember a lot of the properties, right? So what solution I have here is from some other TA who made the question, and some part of it is left out. So all right. Anyway, we'll move on to the next question. I guess that's okay. Next question is on single parity check code. So the question is, an information sequence is encoded using 76 SPC. I'll just write SPC for single parity check code. 76 SPC code, and sent over a binary symmetric channel. I'll write that as BSC. The received sequence is 0 1 0 1 0 1 1. Which of the following statements is true? First option, no error occurred. Second option, even number of errors occurred. Third option, odd number of errors occurred. And the last option is A or B. So either no error occurred, or if there was an error, it should have been an even number of errors. So which of the following statements is true? A 7 6 single parity check code, 6 message bits. For every 6 message bits, there's a parity check bit. So the code word length is 7, message length is 6. So along with your message bits, one bit will be added as a parity condition, as a parity check bit. I'll give you 1 minute to solve it yourself. Solutions manual, I don't have any solutions manual. For this particular course, I just used course material from my own university, and there I didn't have, I didn't read from any textbook. So I just attended lectures and saw video lectures on NPTEL. So the course I saw was from a professor called Andrew Tangaraj from IIT Madras. There's actually another NPTEL course by my own advisor during MTech. His name is P. Vijay Kumar. He was also very good. And those courses, I think those are longer courses. This is an 8 week course, right? Those are even longer. Those are probably 12-week courses. So they have additional material probably. Option D, yeah. So a single parity check code is very simple. You have message bits, right? You have message bits U0, U1, etc. up to UK minus 1, and your parity check bit is simply the sum of all your message bits U0 to UK minus 1. And your code word is, okay, code word, I'll use C instead of V because it's a bit confusing. So your code word is simply P followed by your message bits. So that means if your message has an even number of code words, then your parity check bit will be a 0. If it has an odd number of code words, then your parity check bit will be a 1. Okay. So what does it tell you about the error correction capability? So if there are an even number of ones, your parity will be 0. So the entire code word still has even number of ones, right? If you have an odd number of ones in the message bits, then the parity check bit will be a 1. So together with the parity check bit, the number of ones will be even. So what does parity check bit does is, when you take the entire code word, it will have an even number of ones, right? What does this mean? That means every code word is an even weight code word. So if you receive an even weight vector, that means that either there is no error in the code, or you send some code word and you received a different code word. Those are the only possibilities. So here 0101011 has 4 ones. So the weight of that is 4, which is an even number. That means either there was no error, in which case you had actually sent 101011, right? That was your message, and the sum of all these bits is 0. So your parity check bit is 0. So this is your code word, or some other message was sent, say for example 10100. In this case, the sum of the bits is 0, so your parity bit is 0. So you would have sent this, but two of these would get corrupted to get this received word. That means an even number of errors has occurred. So those are the only possibilities. Okay, so the answer is option D. So this type of code will detect odd number of errors. Even number of errors can't be detected. If you think about it, you can do it the other way also. So suppose this parity check bit, instead of making the number of ones in your entire code word an even number, what if it made it an odd number? That is, if you have some message u0 to uk minus 1, and there are an even number of ones in the message, then I will append a 1 to it. If there are an odd number of ones in the message, then I leave it as it is. So if that happens, would that be useful? That you think about it yourself. Why are they using this type of even parity? Could you make this type of odd parity checker work? That's something you can think of. We'll go to question number 6. Which of the following statements is true about the SPC code? I'll give you the statements, and as I give you a statement, we'll see whether it's true or not then and there. Minimum distance of the SPC code is 3. Is that a correct statement or is that false? So we can use the code word given in the previous example. So if this was your message that has an even number of ones, then you sum that all up, add it as a parity bit. Here the sum of all bits is 0, so your parity bit is 0. Suppose you change this message in only one position. Let's say I change it to the message 001011. Now it has an odd number of ones, right? So the parity bit will also change. And this will be your code word. Now observe that from here to here everything is the same. only two of the bits changed. So these two code words differ in only two places. So the distance between them is 2. So the minimum distance can't be 3. I just gave you an example where the distance is 2. Can there be code words whose distance is only 1? Can the minimum distance only be 1? No, because all the code words are even weight code words. So if you take an even weight code word and change one of the bits, that's an odd weight code word, odd weight vector. So it's not a code word. So if you let's use the previous example itself. So if you take this code word and change any bit, so if you change the parity bit to 1, then this will not be a code word because the parity bit must be the sum of all these bits. But instead of that, if you change any other bit, that will make the number of ones odd. So you'll have to change the parity bit also, right? So the minimum distance of the SPC code is 2 and not 3. So this is a false statement. Second statement, SPC codes can detect all even Hamming weight error patterns. This is also false. We just saw in the previous question how you can not detect even weight errors. So you can only detect odd number of errors. So statement B is also false. Next statement, the generator matrix of the SPC code is given by G is equal to 1 1 1 1 1. Is this statement true? Well, it doesn't seem to be correct because let's see. Here the code word is PU0 U1 UK. If you write that vector form, you must write PU0 U1 UK is equal to U0 plus U1 up to UK minus 1 comma U0 U1 up to UK must be equal to the message times the generator matrix. So the generator matrix here is just a 1 by n matrix. It's also a row vector. So can you multiply a row vector with the row vector? It doesn't even make sense. So obviously that is not the generator matrix of a single parity check code. but it is a generator matrix of a different type of code. Can anyone guess what that is? What is this 111 a generator matrix of? What type of code is generated? Yeah, it's the repetition code. So it's a k by n generator matrix is a k by n matrix where the number of message bits is k, the number of message bits that encoded at a time. So it's a 1 by n matrix. So the number of message bits is just 1. So you just take one message bit, let's call it u, and if you multiply that with 111, what do you get? It's just a scalar multiplied by a vector. So it's u, which is nothing but the repetition code. So the generator matrix of the repetition code is the parity check matrix for the single parity check code. Okay, so all these statements were false. That would mean that whatever is remaining has to be true. So if it's an exam, you don't have to bother about checking whether it's. Of course, it's a good practice to check the other option also. But if you are short on time, you can just mark the remaining option and be done with it. The n plus 1 comma n SPC code is the dual code of n plus 1 comma 1 repetition code. So this is a true statement. So you can check this in different ways. One way to check that is through the dimensions of the generator matrix, or the dimensions of the code. So the dimension of the repetition code is just 1, right? There's just one row vector, and dimension of the SPC code will be equal to n, and the sum of the dimensions is n plus 1, which is the code word length. So this is kind of the rank nullity theorem you study in linear algebra. So rank plus nullity, uh, what was it? I don't remember properly. So that would mean that the subspaces are orthogonal to each other. So a dual code is what? A dual of the code is a set of all code words which are set of all vectors which are orthogonal to every code word. So and that's a dual code. That means, and you also had seen earlier that a set of code words is a subspace of some other vector space. So your k message bits, if you're taking binary numbers, if you have k bits, the vector of k bits is a 2 power k. There are 2 power k possibilities, right? So that these 2 power k messages get mapped to 2 power k messages in a 2 power n vector space, right? In a vector space with 2 power n code words or vectors. So if n is usually greater than k, so the number of vectors in the a number of n dimensional vectors will be more than the number of these k dimensional messages. So there will be more vectors in that space than the code words. So among the remaining code words, if you pick only those code words that are orthogonal to every code word in your code book or code word set, whatever you call it, that will form your dual code. Not sure how much of that you got, but that would mean that this n plus 1 n SPC code is the dual of n plus 1 comma 1 repetition code. Uh, Another way I would think of is so to check orthogonality, you take the dot product of two code words, right? Both code words are of length n plus 1. So you have SPC code u1 to uk minus 1 with the parity bit summation of ui I goes from 0 to k minus 1. That would be a code word in the SPC code. A code word in the repetition code would be of the form some constant, some value repeated n plus 1 times. So to check orthogonality, you take the dot product of the two vectors. The dot product of the two vectors in this case will be c times summation of ui I is equal to 0 to k minus 1 plus cu0 plus cu1 etc plus cuk minus 1. So c times u0, it will be some, these are all in binary, so these operations are in mod 2. Okay, so what is this part? It is simply if you take out c as common, c times summation of ui I is equal to 0 to k minus 1. So it's this sum added to itself. So whatever is this sum is, it could be 1 or 0. If you add it to itself, you will in the end get a 0, right? Or you could think of it in another way to do that is you expand this sum. This is nothing but cu0 XOR cu1 plus cu2 etc plus again you have cu0 cu1 etc cuk minus 1. So in this sum, each of the terms is occurring twice, so each of the terms will add to 0. So if this is 1 and 1, 1 plus 1, you'll get 0 in mod 2. And this you have 2 times. So if it's 0, if both are 0, then sum is 0. Even if it is 1, it gets added twice in the sum. So the dot product of a code word in the SPC and a code word in the repetition code, when they're of the same length, is equal to 0. So that by definition means that they are dual codes. Of course, you would have to, if you have to be more rigorous, you will have to verify that there are no other code words other than the repetition code words in that n plus 1 dimensional space that are also orthogonal to all the code words in SPC. That is, you have to prove that the repetition codes plus the SPC codes make up all the code words in the n plus 1 dimensional space. Okay, this you can try whichever one you want. This is, if this is convenient, you can use that. If this is convenient, you can use that. Whichever method you like. So finally, the answer is this was a true statement. The n plus 1 comma n SPC code is the dual code of n plus 1 comma 1 repetition code. All right. So when you're watching the lectures, try to understand exactly what this code is doing. So just remembering the formulas is kind of pointless. Of course, it's useful for the exams, but even if you pass the exam, if you don't really know what is going on, there's no point in taking this type of course. So whenever you're watching the lectures, try to understand uh, why these parameters are here and why a repetition code is of this form. So you could complete the entire course just by memorizing these formulas, and so repetition code will be of the form n comma 1. If you know that, you could solve a lot of questions about the repetition code, but you should know why a repetition code is of the form n comma 1. You should know what a repetition code is. That's my point. Okay, question 7. Let's see, b n plus 1 comma n minus k Hamming code with parity check matrix H. What is the dimension of the null space of the parity check matrix? What is the answer for this? So it's a Hamming code with code word length n plus 1, message length n minus k. They're asking what is the dimension of the null space of the parity check matrix. Dimension of the null space will be the number of columns minus the dimension of the column space. So the number of columns is n plus 1 minus the dimension of the column space. And for a matrix, the dimension of the column space will be equal to the dimension of the row space. What will be the dimension of the row space and the column space of a parity check matrix of an NK code? For an NK code, dimension of row space and column space will be k. So the dimension of the null space will be n minus k. So here instead of n and k, you have n plus 1 and n minus k. So the dimension it will be nothing but n plus 1 minus, sorry, uh, let me check if what I'm saying is right or sorry. The dimension of the row space is not k. The dimension of the row space is dimension of the row space is n plus 1 minus n minus k, which will be k plus 1. Dimension of the null space is n plus 1 minus the dimension of the column space, which is equal to the dimension of the row space. So it is n plus 1 minus k plus 1, so it is n minus k. So if some in some other question, instead of asking you the dimension of the null space, if they ask you the dimension of the column space or the row space, then you can use this. So I'm not sure what type of question they will ask in your exam. So it's better if you know both of these things. If you know only one of them and they ask you the other in the exam, then you will be in trouble. All right, we'll go to question number 8. Using the code C in question 7, the n plus 1 comma n minus k Hamming code, define a new parity check matrix H1 such that H1 is H with a row of ones. And the question is, what is the dimension of the null space? Null space of H. Of H1. So this we had seen in a previous example, previous problem. We had seen an expurgated Hamming code. So you could get an expurgated Hamming code by adding a row of ones to an already existing Hamming code parity check matrix. And the dimensions of the expurgated Hamming code were, if H was the dimensions of an nk, H was the parity check matrix of an nk code, then H1 was the parity check matrix of an n comma k minus 1 code. So this H, it's actually the parity check matrix of an n plus 1 comma n minus k code, right? So here this is actually n plus 1 comma n minus k code. So H1 will be a parity check matrix of an n plus 1 comma n minus k minus 1 code. So I'll give you 2 minutes to try it yourself. Then I'll come back and give you the answer. Okay, did you try that? Well, to find the dimension of the null space, you follow the same procedure we did here. It's n plus 1 minus the dimension of the row space. Dimension of the row space is n plus 1 minus the message length. So here the message length is n minus k minus 1. So here the dimension of the null space will n minus k. Same procedure you follow if dimension of the null space will be n minus k minus 1. Same procedure as the previous question. The only thing you need to notice that this is an expurgated code, and in the expurgated code the message length is reduced by 1. Okay, so this is the answer, but I'll have to caution you here. The answer in this question was asked in the previous year, or in some year of the course, I think, and the answer was given as n minus k plus 1 instead of n minus k minus 1. So I'm not sure what they used to get to that result, but as far as I know, it should be n minus k minus 1. So there's still a little confusion in this point. I'll try to find out why that is in the next session. So take this answer with a pinch of salt. Not 100% sure if this is the answer or if it's n minus k plus 1. Okay, question 9 is actually very simple. Which bound does an MDS code satisfy? So an MDS code, a maximum distance separable code, and we have studied singleton bound in the class, Hamming bound, and Plotkin bound. Finally, Gilbert, Warshamow bound. Satisfy with equality, not just satisfying. So the MDS codes, it's kind of the other way around. Um, they can uh, flip the question and ask you which code satisfies the singleton bound or which code satisfies the Hamming bound. That type of question can also be asked. Okay. Right here, they are asking which bound does an MDS code satisfy with equality. The answer is singleton bound. And that you just refer to your lecture notes. Okay. It's not that it doesn't. MDS codes don't satisfy other bounds. They satisfy other bounds, not with equality. Okay. Final question on Reed-Muller codes. So they have given two generator matrices. G1 is 1111, 0101, 0011, 3, 5, and 7. G2 is 1111. Okay. And you construct a generator matrix using the previous two generator matrices in the following form. Okay. What are the values of R and M of the Reed-Muller code generated by G? So this G generates a Reed-Muller code. What are its parameters? So first you have to notice that G1 and G2 are also Reed-Muller codes. Okay. G1 is the generator matrix of an RM12 code. Should have seen examples in the lecture. G2 is also an RM code of RM02 code. Okay. So this way of construction is to get a larger generator matrix by using smaller generator matrix. So you construct a larger code by using smaller codes. This type of stuff will pop up often in error control coding. We had seen earlier this augmented matrices, extended matrices. Those are also ways in which you can get a different type of code from an already existing code. So what this will do is, if you have one set of codes, you can get another entire set of codes by following this procedure. So if you just know two or three Reed-Muller codes, you can keep constructing larger and larger codes using the procedure given here. And here, if you have a generator matrix that has parameters R and M minus 1, and the bottom has the parameters R minus 1, M minus 1, this type of matrix will be the generator matrix of an RM Reed-Muller code. So if you compare that with G1 and G2, you have R is equal to 1. So this is R minus 1, and M minus 1 is equal to 2, So I miss 3. So this is m minus 1. This is also m minus 1. So G is the generator matrix of an Rm R comma n is 1 comma 3, 1 3 code. Okay. That's all for today's problem solving session. So here you see, you should know this, that you can construct the larger Reed-Muller generator matrix from the smaller ones, and you should know what are the parameters of that and how you got this and all, even in the previous questions, right? So all these aspects, the theory of those will be covered in the lectures itself. So you have to first see the lectures and then attend the session. In case you don't understand any of the topics in the lectures and you would like me to explain, say if you have some doubts, and I can't do the entire lecture myself, I only have 2 hours. So if you have certain parts of it that you are not clear on, then you can let me know through my email address. I have shared my email address with you. Okay, I'll see you in the next session next week. Yeah, send me a mail if you have any doubts. Thank you.